Right, here we are, week 9, and last week, next week. You'll have your assignment finished by Monday. You'll be so happy and free, and apart from the exams. Alright, so assignment 3 is due on Monday. Help sessions, people say, oh, I don't know when your help sessions are. Special ones I'll post a notice for, but the regular ones are there. So just go to the exams, look at the timetable, and you'll see that there's one at 4 o'clock today, straight after the lecture. And there's another one tomorrow, 1 hour after the lecture finishes. And I'll do a special one. I have a bad feeling there's going to be 100 people outside the door on Friday. And a word of warning, Saturday I won't be around. So Hayden will have to answer all of the forum questions on Saturday. Or Luca. Who is Luca? Is he here or she? Doesn't want to own up. Anyway, he seems to do a good job of pointing you at where the answers are. Because by now we're sort of reaching the point where every new question on the forum has already been asked. Assignment 1, I hate assignment 1. Every time I sit down to do it, someone rings me up or knocks on my door. With any luck, who knows, maybe tonight I can get it finished. But I don't want to make any more promises about assignment 1 marking. My experience, I think, has opened. At the moment, you may be under stress from assignment 3. Don't fill it out now, because you'll think, I hate this course, I hate this course. Wait till you've done the assignment and had a couple of days to settle down and think about it. Alright, so today I'll talk more about relational algebra and kind of how that fits in with how DBMSs are implemented, and either tomorrow or next week we'll talk about transactions and then talk about the exam. But just for fun, here's a little bit of stuff from the exam anyway. So it's on 3rd of December, that's pretty early. Good for me because it gives me plenty of time to mark it. Bad for you because it gives you less time to study. Is that right? 3rd of December? Good. It's pretty bad when you put up an exam time and it's wrong. You get pilloried afterwards. So it's one of the 3-hour exams. It's one of these ones where there's a morning and afternoon session, and I'm sure you've had a look at the selection of those sessions. Not everyone can do an afternoon exam, you know. But if you think that extra 3 hours is going to save your ass, I think you're a bit optimistic. Alright, so standard CC lab environment. In the exam setup that we got, I'll give you access to all of the course notes, not the lecture slides, course notes, which are more detailed than the lecture slides, so hopefully more relevant. Postgres documentation, SQLite documentation, but of course it's a nice lockdown environment, so you don't have access to anything else. So it'll be about 50-50 split. I haven't finally decided yet between SQL queries and written answers. Most likely, unless I discover something remarkable in the next couple of days, that Postgres is usable in the exam environment. I'm a little bit skeptical, and I really don't want to pack everyone onto it and have 250 Postgres servers running at the same time and crashing the whole exam system. Wouldn't be a good idea. So we'll see. SQLite is, as the name suggests, nice light solution. All the queries that I ask will require just standard SQL constructs. So whether it's Postgres or whether it's SQLite, it doesn't matter. If you want to do some practice on SQLite now, You can take a lot of the existing exercises and they'll work in SQLite, so you can play with them. And in any case, you don't have to deal so much with the SQLite interface. Basically, you write your SQL query in something called q1.sql, and then say check q1, and that loads your q1 view into SQLite or whatever and executes it. So you don't even have to deal with the interface that much. So there will be a question drawing an ER diagram that will require you to use dia. If you haven't used that before, you have 14 days or so to learn, and I'll make a video in my copious free time. Ooh, here's a couple of very large database views, and I just realised it might work better if I made the text smaller. So these guys are kind of relevant today because they did an implementation of a very important relational algebra operator, the B tree. So Rudolf Bayer and Ed McCreight back in 1972 came up with this clever data structure which has found its way into pretty much every DBMS currently running, except really crappy ones. Rudolf Bayer stayed in academia and worked in a whole lot of other areas, kept going on the B tree stuff and came up with all these variations on B trees. Also worked in some of the more modern style databases in the 90s, and also did a little bit of work in digital libraries. Ed McCreight went off and worked in the industry for a while and has now retired. So this is the difference. If you go and work in industry, you've got enough money that you can retire early. If you're a sucker and work in academia, you don't have enough money to retire early. Whinge, whinge, whinge. Alright, so let's go and have a look. Assignment 3. I reckon a lot of the questions have been based on a not understanding the distinction between a class and a meeting. A class is something you enroll in, like a lecture, tutorial, whatever. And when I say lecture, I don't mean this, where we're sitting in a room at a particular time. That's a meeting. Effectively, a classroom type lecture is actually a lecture stream. So there are multiple meetings involved. Some other class types, TuteLab is an obvious example, clearly has two meetings. You've got the tutorial in one room for 1 hour, and then you've got the lab in one of the labs in the subsequent hours. So all classes, and as soon as I say that, no, I said typically to avoid the issue of maybe there are some classes in this system that don't have any meetings. Someone I'm sure will find an example as soon as I say all. However, all meetings must be associated with a class. There are lecture web streams that maybe don't have any meetings. If you actually look at the timetable data, web streams are scheduled on Sunday at 6 a.m. So apparently they need to have some kind of meeting info, even though it's not relevant. So class and meeting, different things. And here's an example. How can you spot a class? Because it's got the same class ID as all the other meetings associated with that class. So there's a lecture stream. Can't remember what course this is. There's a different lecture stream. So they've got different tags. They're all meetings associated with the same class. And then you've got all these other classes. So that's, this must be maths. For some reason they have a thing called other. Let's look at something sensible like a tutorial. Does anyone know what that other thing is in maths? No?
It might be like the lab exam.
Oh, really? Oh, I didn't bother to check how frequently it ran. Does it just run in 1 week? Interesting. Right, yeah, possible. In fact, we used to have classes like that when some courses had Friday afternoon prac tests, and they used to get scheduled as a type of class. Then again, as you can see, there's all these tutorials have different class IDs because they're different classes. So generating a timetable, you pick one lecture class, which may involve multiple meetings. You pick one tutorial class. Each tutorial class only involves one meeting in this particular course. There are some courses that have tutorials that have 2 meetings, but it's the same, you know, it's kind of a tutorial stream, if you like, a lecture stream here. So one lecture, one other, one tutorial, and one lecture stream, one other class, one tutorial class, and then work out a timetable based on that. Alright, so this is what I think is the latest things written in the forum or wherever. If you ignore overlapping classes and count, you know, the whole number of hours usage, total number of hours, even though some of them aren't real because you've got 2 classes in the same room at the same time. If you do that, you still get 4 out of 5. If you put in the extra effort to resolve all the overlappings, you get full marks. A valid solution, I think I've defined a couple of times on the website, but basically it's a solution that has one set of meetings for each class type. So if you can do at least that much, then you get that. If you can come up with a solution that has minimal hours, that. If you can come up with a solution that's minimal hours and early in the week, that. Now, given that there are so many solutions, possible solutions, it's going to be impossible to auto-mark, so we'll have to manually inspect them all. So even if your thing looks a bit funny, it's going to be looked at by a human, unlike assignment 2, which wasn't looked at by a human and decided that semicolons are not the same as commas, for example, which is true. So you should have lost marks for that, but you probably shouldn't get 0. Also, ignore web streams, and even if you don't, if you go to all the effort of coming up with a timetable, it's really minimal hours because they take web streams and don't have to come to uni at all, well, except for tutorials and so on, then that's fine, you can do that, but we're not going to test any examples where that's going to be, where that's going to appear. And certainly you're not allowed to have timetable clashes, but Alright, I'd suggest, last week I suggested do as much as you can in SQL, because after all, this is a database course, not a Python course. A lot of people could probably get a fair way with debugging if they asked appropriate types of queries. And asking SQL queries that aren't directly related to the assignment is good practice anyway, so you're not going to do yourself any harm by asking a few queries. Alright, let's get back to relational algebra. So basically, relational algebra is an algebra system where the operands are relations and the operators are things that map one relation to another, or map a pair of relations to a new relation. Let me see, so these are the basic operations: selection, projection and join are the standard 3, plus you can add some others if you want. So select, project, join allows you to do these kind of things: filter out columns, filter out rows, or combine multiple tables. And if you include set operations, then you end up with relationally complete algebra. So in theory, you can answer any data retrieval question in that system. Alright, notation, don't care. We'll see plenty of examples of the notation anyway. Yep, so all the operators return a relation which has a particular schema. Right, so here's one example database. This will recur later, and similarly there's our beers database which will also recur later. Right, I talked about rename, which wasn't one of the main relational operators. We had select, reject and join are the main three, plus the set operators. This one technically is useful because some of the operators are defined saying if you've got this relation and you've got this relation and they have a column in common, then you can do certain types of joins. But if they don't have a column in common, where in common is normally defined as having the same name. If the two columns are obviously related but don't have the same name, then you can use this rename operator to change the name of the column so they are the same. And then you can apply these other things. So really, it's not performing any useful operation. In fact, it's manipulating the schema rather than the data. So it's kind of technically required. So if you really want to follow through using exactly the structure that I've just been talking about, you can use rename to change the names of fields. So there's an example that we've got a table S which has columns C and D, but we want this column to be called CC. So this is actually kind of the opposite to what I was just saying. It's useful to be able to distinguish these two things, and of course in SQL you can qualify a column name by sticking the table name in front of it. Here, if I didn't rename this, then I'd be I'd be specifying the join condition C equals C, which is a little bit funny. So if I change the name to CC, then I can distinguish these two fields. So that gets a little bit tedious, having to stick in all these renames. A little bit of a cheat is to specify the entire result schema on the left-hand side of the assignment statement. And this one, if you look carefully, is actually doing a projection as well. So we're doing a selection from R, which has got columns A, B, C. We're using the value in A to determine which tuples to choose, but then we're chucking away the A value. That will also get rid of duplicates, remember, since the relational algebra strictly deals with sets, not bags, which is what SQL uses. And here's another example. So this is really just a straight rename. S has got C and D. We want to call those columns C, C and D. And then we can join those two intermediate tables to give us our final result. So this whole approach here might look vaguely familiar because you can kind of think of each of these rows or each of these lines as a view, defining a view. So this first one defines a view based on a select. It's not a particularly interesting view because it always uses the same value to determine the filter. This one is, once again, not a super interesting view because all it's doing is renaming the columns. And this one, okay, that's our result view, so that's potentially useful. Alright, so selection basically runs to a table, looks at all the tuples in the table, and if a tuple satisfies the selection condition, then it gets added to the result. So here's some examples, getting all the tuples where B is equal to 1, getting all the tuples where the B column has a value greater than or equal to the D column, and getting all the tuples that satisfy that condition. And it's perfectly possible that you can specify a condition such that no tuple meets that condition, therefore the result set is going to be empty, which is what we've got there. Alright, I decided I'd have a look at how we might answer some of the old queries that we did with SQL and implement them in relational algebra. So, if we had a query that says, give me the details of all the bars that are located in the rocks, as soon as it says details, if the user isn't going to be more specific about what information they want, then you just assume they want everything. So there's no projection involved, so it's a straight selection. That's the selection condition. That's the table it's selecting from. So it's going to get all of the bars whose address happens to be the rocks, and that's our result set. Beers that are made by Sierra Nevada, well, we can do a selection to extract just those beers into a new table. If you want, you could have a view called SN beers, and then we project out just the name and call it, change the column name to beer. So it's pretty easy to see how you do that in SQL, but let's just take a look how we might. Lectures. Started on this. So all the details of all the bars in the rocks, that's the relational algebra in SQL. You can select everything from the bars table where the address is in the rocks. Of course, you can see there's a little bit more syntax that we need to apply here, and if we wanted to, we could turn that into a view. Beers made by Sierra Nevada. That first line, you could make it into a view, or you could do the whole thing as a single query by expanding this by that value there, by that expression there. And in fact, that's what certainly Postgres does. When you use views in a select query, it doesn't actually, if you like, invoke the view at any point. What it does, it actually takes the definition of the view and sticks that into your SQL statement and processes the whole thing as a single large SQL statement, if you like. We'll see how it actually processes stuff later. But let's imagine that we are going to do as a single thing. Ooh, that wouldn't have mattered. So we want to select name as beer. So what we're doing there is basically that part. And then we need from the beers table so we could do it as a single thing, and basically what I've done, if I stuck that in there and replaced that by that definition, I get the same thing. So the syntax looks a bit different, especially the order that you got things, and some operators, you know, don't kind of appear renamed to some extent. Is as projection is basically based on what columns you put in the select statement, and the selection operator is handled by the where clause. Right. So that's selection. Projection basically says I want just some of the columns from the table. This is actually, I should have looked at the previous example, but if you do a projection, you might think that you're going to get the same number of tuples, but something the projection actually does is it removes duplicates. So if by doing a projection I ended up with two tuples that look the same, let's say I project the name of students. Okay, I project student name from the student table. So obviously the student table is going to have all the ZIDs, they'll all be distinct. All the names, there might, and highly likely, be two students with the same name. Obviously they can be distinguished by the ZID, but if you were to project that table just on the student name column, then you're not going to end up with two John Smiths, you're only going to end up with a single entry for John Smith. So part of projection in the relational algebra is to remove duplicates. So there are no duplicates because it's a result set. Relational databases don't implement set semantics, they actually implement bag semantics. So you would have two entries for John Smith if you did a select name from student table. So the size of the result would always be the same as the size of the input. Of course, if you're doing a projection of a primary key, for example, you're clearly going to end up with the same number of tuples in the result table as in the original table, because all of the values in the primary key column are distinct. So there won't be duplicates. Right, so here's some examples and you can see what happens. Here I've got this table, it's got duplicate values in column D, so when you do the projection, you get rid of them and you end up with just the unique values. Projecting B and D gets rid of some because there are two tuples that have 1 and 4 as the values for B and D, and in the result we only want one of those tuples. And of course any projection that involves the A column, which is a primary key, is going to end up with the same number of tuples as the original table. Alright, so here's some more examples of using projection to solve problems. What are the names of all of the beers? So I just project the beer name column. Names of drinkers who live in Newtown, well, I have to do some filtering and filter out just those drinkers who live in Newtown, and then project out the drinker name because that's what the request asked for. And what are all the breweries? Well, presumably, if they're not going to give us any more information, maybe they just wanted the name of the brewer so we could project our manufacturer. But notice here that I've slipped in a rename so that rather than having Manf as the name of the attribute, it's now called brewer. Let me have a quick look at the SQL versus relational algebra. Names of all beers, project name from the beers table. If you really want to follow exactly the semantics of the relational algebra, then you really should put distinct. So if there happen to be two beers with the same name, you'll only have one instance of that name in the final table. Names of drinkers who live in Newtown. So that's just that. Once again, if you wanted to honour the semantics of the relational algebra, you put distinct there. Otherwise, if there are two drinkers called John who live in Newtown, you'll get two tuples, one for each of the Johns. And what are all the breweries is just a projection plus a rename, so select man as brewer for beers. And once again, in this case, it's unlikely that two brewers would have the same name, but you can always make sure that you eliminate duplicates by doing that. Right. Union is standard set union, yep.
What if you project two columns? How do you distinct that and this the other?
Oh. I think you just put a comma, distinct column A, comma, column B. I think that applies across the whole thing. Of course, a question like that you can always answer by starting a database, but unfortunately I don't have a database running at this point. I can always start one. That's probably not a great choice. Have I got a simple database? I'm guessing that's this one. Let's so select distinct. So the distinct seems to apply across all of the.
That could just be distinct A.
What?
That could just be like one A's.
Oh. All right. You reckon? So make a suggestion as to how I should populate this so I can discover whether that's true. I know. Right, so if it really is just distinct A, I'll get 4 results and look like an idiot. Alright, good point. Let's see. I've seen that syntax before. No. Don't know. You'll have to play around. No. Can't think off the top of my head, so have a look online and see what you can find. Right, so union is a set based operator. So this does do distinct properly. Hey, wait on, wasn't that correct? That was what we were supposed to get. Yeah. Right there. Let's try that one. Does that prove it? I don't know. In any case, let's continue. So union does have a notion of distinct. If you take a union of two things, you're not going to have any duplicates in the result. The other thing about these set operations, the two tables have to have exactly the same schema. And in the context of relational algebra, that really means same attribute names in the same order. So it could be R, ABC, S, ABC, and you'd be able to union them. Similarly, intersection once again requires them to be compatible in the sense of having the same number and the same named attributes. That's called union compatibility. And that's the definition. So you start out with an initially empty set. You look at all the tuples in R. If they also appear in the other, in R1, if they also appear in the upper table R2, then they end up in the results set. So it's standard definition of intersection. So there's intersection and union. And you can see that the union here has removed that duplicate A1X4 combination. So it only appears once in the result. And these were the examples that we had for bars were either John or Gernot drinks. And I think, if I remember correctly, we might have done both of these as views, and then we did a union on those views. We don't necessarily have to do them as views. We could simply interpolate that whole expression, or the SQL of that whole expression, into there. And similarly, bars where they both drink, you take the intersection of those two. Set difference finds tuples in one set that don't occur in the other set. Once again, this is a set type operation, so the two tables have to be union compatible, and that's basically the definition. So start from R1, look at each tuple in R1. If it doesn't occur in R2, then it ends up in the result. And there's some examples, and obviously it's not a symmetric operator, unlike union and intersection where it wouldn't matter what order you put the tables in the relational algebra. Querying with the difference operator. So if we take John's bars and Gernot bars, then we can use difference to answer this question. Here, SQL, the syntax for difference in SQL is except, the word except. So you put your expression giving a table, and then except an expression giving another table. So rather than just typing minus. And another example, bars that sell VB but not new, find all the VB bars, find all the bars that sell new, and take a set difference to get the final result. Yeah, alright, maybe I will have a quick look at how you do that in SQL. So let's skip over those. Bars where Gernot doesn't. Alright. So without defining any views, we could do it like this. From bars. So, a couple of things to notice. These two selection clauses must produce the same set of attributes. So here we're just taking the bar name from the bars table. We're filtering out some set of bars, and we're filtering out a different set of bars there, and then we're taking the difference. So that would apply equally well to that VBU example. Alright, a relational algebra construct that's never used in practice because it produces gigantic results is product. It's easy to accidentally do a product if you mess up your join condition, or even if you leave the join condition out, that will produce a product. And the reason why a product is not helpful is that it gives you every pair of tuples from both tables. So we take a tuple from one table, take a tuple from another table, merge them into a single tuple. So clearly we're going to end up with a result set that's the product of the two sizes. So if both tables have 1,000 tuples in, then we're going to end up with 1,000,000 tuples in the result of the product. So if you accidentally produce something like that and you've got tables that are larger than 1,000, potentially you're going to generate a very large intermediate result, which Postgres will happily deal with, but will take a long time to process. So if you accidentally do that, then you might end up sitting there for a long time looking at the screen, waiting for it to give you a result. So here's an example of a product on two small tables. So all of the columns from both tables end up in the final result, and every pair of tuples from the two tables. So AMX gets combined with both of those for the first two tuples. EKY gets combined with both, and so on. I didn't have any example of using a product because it's not a particularly useful thing to have. So the join operator is really the thing that puts tables together. In some sense, product does, but not in a useful way. So a natural join is, if you like, a specialised kind of product that requires the two tables to have a common set of attributes. And the strict definition is the attributes have to have the same names. Therefore, you might need to do a rename if they didn't, but you still wanted to merge the two tables. So imagine we've got tables R and S. They've both got attributes KLM. If I do a natural join on those two tables, then I'm going to check a matching condition which says the K value in tuple 1 is to be the same as the K value in tuple 2. The L values have to match and the M values have to match. And if that's the case, the way natural join works is it says, well, the K value here is the same as the K value here, so there's no point keeping both, so it'll only keep one. So it only keeps one column from each of the common attributes. So it's different to join, to product. In the previous example, that would keep, if we did a product of these two tables, we have A, B, C, D, F, G, J, K, L, M, N, blah, 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 up to X, Y, Z. Whereas natural join will throw away one of the pair of common attributes. Right, so here's an example, ABC and CD. We do a join, so we end up with ABCD. There's only one tuple that joins with that, and one tuple that joins with that, and EKY misses out because it doesn't have a C value that corresponds to any C value in this table. The most common kind of join is a theta join because it allows you to specify the join condition. You can specify the other two things that we just looked at by a combination of join condition and projection. So, product, if you specify the condition as true, then it's going to produce a product. Not useful. If you specify the condition as the equivalent of that matching condition that we had for natural join, and you also do a projection to get rid of one set or one of each of the common sets of values, then you can produce natural join from theta join plus projection. So this is the standard join that we've been using all throughout term. Here's an example. You can see the joint condition isn't always equality, can have some other kind of condition. Often it's equality, especially when we're trying to put together two tables based on a primary key, foreign key combination. You'll invariably have an equals there. So theta join is the most frequently used join. Is there anything interesting here? C has to be strictly greater than D. So X isn't strictly greater than any D in that table. Y is greater than X and X. And Z, assuming we're doing lexical ordering, is greater than all of them. So you're going to end up with a combination of all of these three tuples with FPZ, a combination of two tuples, the two tuples having X for the D value for that. So if we were to look at these kind of examples that we had, clearly you've got to have a join. So here we might say, all right, I'm only interested in the Newtown bars. That's going to become a new table, a new temporary table, if you like, with a single attribute n bar. So we do a join bar against n bar, and then we project out just the drinkers. So we select the bars that are in Newtown. We do a join with the bars that the drinkers go to with the Newtown bars, and then just project out the drinkers that are left. And similarly, we could do Who Drinks Beers made by Carlton. So I guess we could, and you know, the queries are going, the SQL is going to come out of these. Looks pretty much like ones that you've been playing around with. So let's do this. Select drinker. And I think that's unambiguous, but I'll stick in. So the likes table with the beers table, and here I'm not producing that Carlton beers intermediate result on notice here we don't have to have the attributes having the same name. So hopefully, unless I've stuffed something up, that would be the equivalent of this relational algebra stuff up here. Yep, looks kind of right. Right, so theta join is the one you've been using all term. And the final relational algebra operation, non-standard, but useful, although the implementation in SQL is interesting. The division operator basically allows you to search for tuples, or to search for a column. Let's have a look at the example. It's easier to explain with an example. So here we got this table that has 4s, X, Y, Z, 5s, coupled up with X, Y, Z as well. And here we've got a table with one of those tuples missing, so the 5Y tuple. And another table that's just got X and Y. So if we do a division on R and T, so what we do is we look through this table and we look for particular A values that occur in conjunction with all of the values in the T table. And if we find such tuples, or if we find such A values, then they end up in the final result. So we can see here that 4 occurs in conjunction with X and Y, which is what we're looking for. So 4 is going to end up in the final result, and the value 5 occurs in conjunction with X and Y, so that ends up in the final result. However, if we take S divided by T, then we're looking for values in the A column that occur in conjunction with X and Y. Well, 4 does, because we've got X and Y, but 5 doesn't, because there's no 5Y. Therefore, 5 doesn't end up in the result of the division, but 4 does. So, what use is that? It's very commonly used in queries that have the notion of for all or for every or something like that. So, for example, which beers are sold in all bars? Okay. So, you get a table of beers and bars where they're sold, so that's easy, that's just a projection from the sold table, and basically the only reason we even need a projection here is that we're getting rid of the price value, the price column, and then generate a relation that contains all of the bars. So if we want, we can do something like this. So produce a table which has a single column called bar to match up with the name of the column here, and that comes out of the bars table. So we're taking every bar and putting it in a table with a single column called bar. And having got these two things in sync, if you like, that was the other thing I should have said back here, the column that we've got here has to match one of the columns that we've got here. And once again, that's technical, you can do a rename in relational algebra to make that match up. So then you can do that as to produce your final result. Take all of the beers that are sold in bars, and then divide by the total number of bars. So the only tuples that are going to end up in the final result are tuples in R1, where we have a beer that occurs in conjunction with every bar that occurs in the R2 table, and the R2 table contains every bar. Okay, so that will give us our final result. Perfect, good point to stop. Alright, so let's have a break and then I'll talk about DBMS architecture.